Okay, so it's that time again for the next PHYS 121 video. Last time what we were talking about was trying to understand how a current can generate a magnetic field. I would say that's the important thing. So we saw that if we had a current in a wire and we placed a compass, a magnetic needle near that wire, the current, when it's on, would deflect that needle. And we developed this right-hand rule, so if we put our thumb in the direction of the current, then we found that our fingers would curl around in the direction of the magnetic field. So if this was the current, then the magnetic field, by the right-hand rule, would loop around in the direction that I've drawn here. And so that was all a qualitative description, and what I want to imagine now is, well, what I want to see if we can come up with a quantitative description of the magnetic field produced first by a moving charge. And so the scenario I want to imagine is that we're going to take a charge and we're going to accelerate it up to some velocity. And so how could we do that? We could imagine taking a parallel plate capacitor, and let's make this the negative plate. So we put some negative charge over here and we put some positive charge over here. And then what we're going to do is we're going to place an electron between these plates. And so let's say this is an electron, and we know that the electric field is going to be in the direction from positive to negative, and so it'll exert a force on our electron that will be in the opposite direction of the electric field. So this is the force on our electron, and this is the electric field. And so then our electron accelerates towards the positive plate, and then what we're going to do is we're going to drill a small little hole into our positive plate. Oh, so I didn't want to delete the whole plate. But let's say we leave a little hole in our positive plate so that when the electron reaches that plate, it just exits the hole. And for a capacitor, the electric field is 0 outside, and so now our electron moves with some constant velocity. Okay, good. And so we have some charge of minus E moving at a constant velocity. Then what we're going to do is we're going to try to determine the value of the magnetic field at some point P. And so what we might do is we might place a compass. In principle, we could do this. We could place a little compass at point P, and we could see which way the needle deflects to determine the direction of the magnetic field. And we could try to turn the needle away from the direction it wants to be and figure out how much force or how much torque do we have to put on the needle in order to move it away from its preferred direction. And that could be a measure of the strength of this magnetic field. Okay, so by the right-hand rule, if we put our thumb in the direction of the current, and so we have to remember now we're talking about we have an electron, and so the current is in the opposite direction of the electron velocity. So the current would be towards the left of the screen, from right to left. And so we put our thumb in that direction, curl our fingers, and at point P, we would find that the magnetic field, B, is into the page. Okay, so we already knew that from the right-hand rule. But what we'd like to try to do is we'd like to try to determine the magnitude of this magnetic field. So we could do a couple things. We could do this for our electron But what we do is we do this for a bunch of different charges on our capacitor plates. And so if we start with a certain charge, plus and minus Q, then we get a certain velocity, and we measure the strength of the field. Then what we do is we say double the charge. So we have minus 2Q and plus 2Q on our capacitor plates, and so the velocity increases. When the velocity increases, what we find is that the strength of the magnetic field increases in proportion to the velocity. Okay. The other thing we might do is we say we might measure the strength of the magnetic field at different points. So different distances r between our observation point P and the position of our electron. And if we did that, we would find that the strength of the magnetic field is proportional to 1 over the square of that distance. The other thing we could do is we could not use an electron, but we could use a different charge. So for example, what you can do is you can take a helium atom. So a helium atom has 2 protons and 2 electrons. And if you strip off the electrons, you're left with just the helium nucleus. It has a charge of plus 2. It's called an alpha particle. And so what we could do is we could put an alpha particle between the plates of our capacitor. We would have to switch which plate is negative and which one is positive so that we'd accelerate it in the right direction. And suppose we got the alpha particle moving with the same speed as the electron, and we measured the strength of the magnetic field at the same distance r. What we would find is that the alpha particle would make a magnetic field that's twice as strong as the electron. And so that's because the alpha particle has twice the charge of the electron. So the magnetic field's also proportional to the charge Q. Just to make the point, the alpha particle would also reverse the direction of the magnetic field. So by the right-hand rule, if we have a positive alpha particle moving from left to right, then by the right-hand rule, our thumb points to the right edge of the screen and our fingers curl out of the page at point P. Okay. Now, there's one other little subtle dependence on the strength of this magnetic field, and it has to do with the angle theta between our velocity vector and, let's say, our position vector that goes from the charge to our observation point. It turns out that this magnetic field strength is also proportional to the sine of this angle theta. That's kind of interesting because what it tells you is that for a fixed distance between the charge and the observation point P, the magnetic field changes depending on that angle. So sine theta is a maximum at 90 degrees. And so what that means is if we had our moving charge, let's go back to the electron, and we went a distance r away to some point, and so this is a 90-degree angle. This is where you would get a maximum magnetic field for a fixed distance r. But then if we took this constant radius, so it traces out like a section of a circle, then we would get over here for a different value of theta, we'd get some, say, medium value of b. And then over here, where theta equals 0, we would get b equals 0. So this is the theta equals 0 case. This is the theta equals pi by 2 case. And this is the theta is between 0 and pi by 2. Okay, so and that's what we would find if we did that experiment. The constant of proportionality is written in terms of this factor mu naught. So if we insert a constant of proportionality, it's written as mu naught over 4 pi. And so this thing is going to be our constant of proportionality. Okay. Whoops, sorry, I didn't want to do that. And so then we put in our Q, which size pen was I using? So we put in Q V sine theta over R squared, and this is the magnitude or the strength of the magnetic field for a charge moving at speed v, where the observation point is a distance r away, and the theta is the angle between vector v and vector r. So theta is the angle between the velocity vector and the position vector. Okay, so the other thing I guess we could say is that the direction of the magnetic field is determined by the right-hand rule. Okay, so maybe what we should do is just say that mu naught is called the permeability of free space, and it has a value of 4 pi times 10 to the minus 7, and the units are Tesla, meters per amp. Okay, so let's just do a dimensional analysis, a unit analysis of this expression above. So we are interested in the units of B, which are going to be the units of mu naught, which we said were going to be this kind of Tesla, whatever that is, meters per amp. And then we have Q, which is in coulombs. Then we have V, which is in meters per second. And then we have 1 over R squared. So all the meters cancel, and so we get a Tesla 1 over amp coulombs per second, but a coulomb per second is an amp, and so we cancel these, and so the units of our magnetic field are in Tesla. So T is a Tesla, and 1 Tesla is equal to 1 Newton per amp per meter. Okay, good. Now, let's go back to this expression. There's a lot of information contained in here, and what we would like to do is we would like to see if we could express all of this information, the information about the magnitude of the field, magnetic field, and also the direction of the magnetic field in a single expression. Okay, and actually, before we do that, let's just draw one picture. Let's imagine that we've got a positive charge moving along this line, and it's moving with some velocity v. So what we found is that by the right-hand rule, we'll get a magnetic field that loops around this line, and it will be in this kind of direction. Okay, and then if we move further away, where r gets larger and then also theta gets smaller, then that tells us that the strength of the magnetic field would decrease. And if we go behind the charge, the strength of the magnetic field would also decrease. Okay, good. So we want to see if we can express the information. Mu naught over 4 pi is what we wanted. So mu naught over 4 pi, and this was v and q and sine theta over r squared. I think that's everything. So can we write a vector equation that includes information about the direction of B? So that's the real goal. Okay, and so to do that, what we're going to have to do is maybe we'll start a new page. What we'll have to do is we'll have to introduce something called the cross product. And so the way we're going to write the cross product is we're going to write the cross product of, say, vectors C and D. So the cross product between vectors C and D is written as C cross D. Now, we have come across a vector product in the past, and it was the dot product. So let's just recall the dot product. So if I took the dot product of vectors C and D, what we said that was equal to was the magnitude of C times the magnitude of D times the cosine of the angle between them, right? And so if this was, say, C and D, then theta is the angle between them. What's nice about the cross product is that it has a similar calculation for the magnitude. The magnitude of C cross D is, so I'm going to write it like this. So these vertical lines mean I just want the magnitude of whatever this vector cross product is. In many ways, it's like the dot product in this case. The only difference is instead of taking the cosine of the angle between the vectors, we take the sine of the angle. You could see that that's going to be useful because when we were thinking about the magnetic field, what we had was a sine theta. So maybe we can somehow use this cross product to insert the sine theta into our expression. There is, however, a very important difference between, say, C dot D and C cross D. And so the difference is that the result of C dot product with D is a scalar quantity. Scalar quantity means just that it's a number without any associated direction. So it's not a vector. associated direction. Okay, so it's not a vector. So the dot product is a product between two vectors, but the result is not a vector. In fact, we already know this because we have used dot products to calculate the work by a force F during, say, a displacement. So in general, what we said is the work is equal to the integral of F dot ds. And the work kinetic energy theorem says that the work is equal to the change in kinetic energy. And so here we have a dot product between two vectors, a force and an infinitesimal displacement, and the result is a scalar, or in this case for the work, it's an energy or a change in energy. So there's no direction associated with that energy. Okay, but if we go back and look at the cross product, it turns out that the result of a cross product is another vector. The result of a cross product is another vector. So in fact, what we could do is we could say, let's say vector A is C cross D. And so what we need to do is we need to figure out the direction of vector A. We already know that the magnitude of A is just going to be the magnitude of C times the magnitude of D times sine theta. But we need to determine the direction of A. And so the way the direction of A is defined is that, one thing about it is that A is perpendicular to C and A is perpendicular to D. So that actually restricts the direction of A quite a bit, because if we were to, let's take an example. Let's take XYZ coordinate system, and what I'm going to do is I'm going to take, say, a vector C. I'll put it on the y-axis, and then let me extend the x-axis back here, and what I'm going to do is I'm going to take a vector D and I'm going to put it in the negative x direction. So what that means is if A, which is the cross product of C and D, is going to be perpendicular to both, it has to be either in the plus z or in the minus z direction, right? It's either in this direction or it's in this direction. That's the only way that it can be perpendicular to both C and D. And so I could have drawn any two vectors C and D, and what we would find is that the result for A would have to be in one of two directions if it's going to satisfy both of these conditions. Okay, so we need a mechanism for determining that direction. And what we're going to have to introduce is a second right-hand rule. So the direction of A equals to C cross D is determined by a second right-hand rule. So right-hand rule, I'm going to use RHR, and this is going to be right-hand rule number 2. Again, this is something that would be nice to stand in front of you and show it to you how it works, and then better than that, force you to try it for yourself. But in our current circumstances, I can't do that. So I'll write it out and I'll try to draw a picture that will probably be a bit of a disaster. But anyways, let's write out what you do. So the first step is to put your right arm, in the direction of C. Okay, so as a picture, what I'm going to do is I'm going to try to take my arm and I'm going to put it in the direction of C. So there's my arm. This is the wrist where it gets a little bit more narrow, right? Okay, good. Done. So C is along the y-axis, which is to the right of the screen. And what we're going to do is we're going to curl our fingers in the direction of the second vector, right? So C is the first vector in the cross product, and D is the second vector in our cross product, right? We wrote C cross D. Okay, so now we take our fingers and so we move them and we put them in the direction of, let me try that again. So I'm going to take my fingers and I'm going to curl them so that they're in the direction of D. And D is this negative x direction. And what will happen is that your thumb will point in the direction of C cross D. So your thumb points along the direction of C cross D. Okay, so what we've got here is our arm is in the direction of C. Our fingers are in the direction of D. And our thumb gives the direction of C cross D. So we would get C cross D here. Okay, while we're doing this, let's see what would happen if we did the opposite of C cross D. What if we did D cross C? Okay, so let's next consider, say B is D cross C. So if we follow the right-hand rule, we would have to put our arm in the direction of D, and so this is going to be tricky to draw again, for me anyways. Put our arm in the direction of D, and we want to curl our fingers in the direction of C, and our thumb is going to point in the direction of C cross D. Okay, and so let's see, we start by putting our arm in the direction of D, then we red vector for C, our fingers are in the direction of C, and then our thumb is in the direction of, this would be B, is equal to D cross C. And so I'll do that as a dashed line maybe. So B is equal to D cross C. Okay, and so what we can obviously see is that A and B are in opposite directions. So what we found by our right-hand rule is that this is equal to minus A. And so what we find then is that C cross D, which is A, is just exactly opposite of D cross C. And so that's kind of a funny result. Usually in multiplication, the order of your factors doesn't matter, right? If I take 2 times 4, that's the same as 4 times 2. That's also true for dot product. If I take A dot B, that's the same as B dot A. Cross product, we have to be careful. So the order of the vectors in the cross product matters. Okay, so let's get back to our Biot Savart Law and see why this cross product stuff is relevant. So we take our charge, say some charge plus q, and it's moving with some velocity v, and then we go out to some observation point p, and by the right-hand rule, put our thumb in the direction of v for the positive charge. Our fingers curl out of the board, so B is out of the screen. Okay, now let's define a unit vector r hat. So r hat is a unit vector that is in the direction of the position vector r. In fact, what we could do is we could write the position vector r as some magnitude, the distance between q and point P, and it's in the direction of r hat. So consider now an angle theta between v and r hat. If we then were to calculate v cross r hat, that would have a magnitude equal to the magnitude of the velocity times the magnitude of r hat times the sine of the angle between them. But r hat's a unit vector, so it has magnitude 1. The magnitude of vector v is just, say, v, and so we get v sine theta. That's kind of nice, actually, because v sine theta appears in our Biot Savart law. Let's also think about the direction of v cross b. The direction of v cross b, sorry, not, is v cross r hat, sorry, v cross r hat. By right-hand rule number 2 is, so what would we do? We'd put our arm in the direction of v, and we would try to curl our fingers, so that's, v is to the right of the screen, so that's the direction of our arm, and we'd curl our fingers just a little bit so that they're parallel to r hat, and our thumb points out of the screen, is out of the screen, i.e. in the direction of the magnetic field. So what we could do is then our vector version of the Biot Savart Law is B is equal to mu naught over 4 pi was our constant of proportionality. And then we said there was Q, and then there was V sine theta, but we saw that we could write V sine theta as V cross R hat. And so that gives us the right magnitude, V sine theta. It also gives us the direction of the magnetic field, and then we divide by R squared. And so this is the vector version of the Biot Savart law. So this is the magnetic field due to, so magnetic field due to a moving charge Q. All right, good. So let's do a couple other things. Let's leave this Biot Savart law for a second, and let's just do some practice with the cross product. What I want to do is I want to take some cross products of unit vectors. So I'm going to say I hat is in the x direction, j hat's in the y direction, and k hat is in the z direction. So let's first figure out, say, the magnitude of some cross product between unit vectors. So the magnitude of I hat cross j hat. Well, the magnitude is just the magnitude of I hat times the magnitude of j hat times the sine of the angle between them. But all of these unit vectors are mutually perpendicular, so the angle is always going to be 90 degrees. But the magnitude of a unit vector is 1, and the sine of 90 is 1. And so the magnitude of the cross product I hat cross j hat is going to be 1. And I could have chosen any two different unit vectors. Notice I said two different unit vectors. Let's see what would happen if I took a cross product of a unit vector I hat with itself. And so if I just want the magnitude, it would be the magnitude of I hat times the magnitude of I hat times sine of the angle between I hat and I hat. Well, those are parallel vectors, and so the angle between them is 0. So we get 1 and 1 for the magnitudes of I hat, and then sine theta becomes sine of 0, but sine of 0 is 0, and so this is 0. I could have chosen, say, I hat cross with minus I hat. Those would be anti-parallel vectors. So the angle between them would be 180 degrees, and the sine of 180 is 0. So what we can deduce from this is that the cross product between any parallel or anti-parallel vectors is 0. Okay, good. So let's just run through some of these. I hat cross j hat. So you should practice this. Do this for yourself. Put your arm in the direction of I hat, which, if you like, is out of the screen. I can't obviously draw it that way, but that's what it's intended. It's out of the screen. Curl your fingers in the direction of j hat to the right of the screen, and your thumb should point to the top of the screen. And so we get k hat. So we already worked out that if we switch the order of the vectors in the cross product, we just get a minus sign. And you could confirm that by right-hand rule. Put your arm in the j hat direction, curl your fingers in I hat direction. It should point your thumb should point to the bottom of the screen. So we could do I hat cross K hat. So I hat cross K hat. So your arms out of the screen, your fingers go to point towards the top of the screen, and your thumb should point to the left, and that's the minus J hat direction. So that means if we swap K hat and I hat, we pick up a minus sign, so we get minus J hat, which is plus J hat. And then J hat cross K hat. So J hat cross K hat, by right-hand rule, that should be plus I hat. And then if we switch the order, we should get a minus I hat. Okay, good. And so if you can get comfortable with quickly doing the cross product between unit vectors, then I think you will have mastered this right-hand rule number 2. Okay, so the last thing I want to do today is I want to see if we can modify the Biot Savart Law so that we can calculate the current, calculate the magnetic field not due to just a single point charge, Q, but to a current, say the current in a wire or something like that. So the next topic is the magnetic field of a current. Okay, so we know that the magnetic field due to a point charge is this Biot Savart law. It's what we just worked on. You know, it's a little bit of an intimidating equation maybe because it involves this new cross product, and it's a cross product with a weird unit vector. Nevertheless, that's what it is. Okay, so then what we do is, let's imagine that we have a length of wire, and we're going to try to determine the magnetic field at some point P out here, P. And this is a distance r away, and we have our unit vector r hat. So what we could do is we could say, well, if there's a current I in this wire, what we might do is we might take a little segment of this wire, and so maybe we could color it in a little bit. And so we're going to take this segment of the wire, and we're going to figure out how much charge is in that segment of wire, and then could we go back and use the Biot Savart law, it's right here, this Biot Savart law, to determine the magnetic field at P just due to that little segment. Okay, so how would that work? Current is delta Q divided by delta T. And so I'm going to do something weird. I'm going to just take this delta Q divided by delta T, and then I'm just going to multiply by 1. But I'm going to write 1 as delta S over delta S, where delta S is just the length of this little segment that I shaded yellow. Okay, so then we could reorder the factors. We could do it like this. Delta Q over delta S, and then delta S over delta T. And so what we're imagining is some charge has moved a distance delta S in time delta T, so that means the speed is delta S divided by delta T, and so we write that as current is now delta Q divided by delta S times the speed. So therefore, delta Q times V is equal to I delta S, or we could say delta Q and vector V. So now what we've got is a charge moving with velocity V along our wire, but that's parallel to the displacement delta S. And so we could maybe let me clean this up a little bit. So this is our wire, this is the vector V, and what I want to do now is take this delta S, and now instead of writing it as just some length, we can say it's also in the direction of the wire. And so the velocity and delta S are in the same direction, and so I could write a vector equation like so. So the plan is to go back to our Biot Savart Law and say, well, I have a QV here, and what we've done is we've calculated a new way of expressing Q times V in terms of a current and a displacement along our wire. Okay. So therefore, the magnetic field due to, so this is going to be a weird notation, but this is a short segment of current, is going to be the prefactor, this constant of proportionality hasn't changed, mu naught over 4 pi. But instead of writing QV, I'm going to write I delta S. And then the we still have the cross product with r hat and divided by r squared. And so this is the magnetic field due to a short segment of current. So this is roughly where I'm going to stop, but let me just preview what we'll think about next time. So the picture above is not a short segment of current, it's a long wire that has current, and we now know how to calculate, say, the contribution of some little section, delta S, of current a distance r away to some observation point. And so this is the magnetic field at P due to segment delta S of our wire. But there's a whole bunch of segments of this wire, right? And so we could put them all a different color. And if I want to know what is the total magnetic field at point P, I have to add up all of the contributions from all of the different segments. So the net magnetic field at P is B net is equal to the sum over all segments BI, like so. And so inside that sum, we're going to have this expression for all of the individual little segments. And so maybe that'll be our starting point next time. Next time, we'll start with find the net magnetic field at P due to a long current, a long wire with current I. All right, thanks very much, and we'll see you next time.